we're now going to introduce a key analytic tool for studying probability measures, and in particular, their weak limits. And that is, in probability circles, known as the characteristic function, more generally called the Fourier transform. Let mu be a Borel probability measure on Rd, and for each xi in Rd, define a complex valued function mu hat on Rd by this integral. Using the notation from the last lecture, this is the integral of e xi d mu. The function e xi here, this trigonometric polynomial, is bounded and measurable since it's continuous, and therefore is in L1 of mu for every probability measure mu. And so this defines a bounded function of xi. It is called the Fourier transform of the measure mu. Now, if x is a d-dimensional random vector, meaning that its law is a measure mu x on Rd, then we define the characteristic function phi sub x of that random variable to be the Fourier transform of the law of x. Using the change of variables theorem, we can write that in this nice form. Phi sub x at a vector xi is the expectation of e to the I xi dotted with the random vector x. Now, in our last lecture, we used the complex version of Dynkin's multiplicative systems theorem to show that if two measures give the same integrals against all of these trigonometric polynomials, then they are in fact the same measure. In the current language, what that says exactly is that the map that sends a measure mu to its Fourier transform is injective. Indeed, this is mu hat of xi, and this is nu hat of xi. And so if mu hat and nu hat agree at all points xi, it follows that mu is equal to nu. So in principle, we can recover any probability measure from its Fourier transform. Now let's compare that to a very closely related analytic transform we've worked with before, the moment generating function. Indeed, there's very little difference in appearance of the formulas for the moment generating function and the characteristic function of a random vector or a random variable. In fact, superficially, we could write that the characteristic function of x at xi is the moment generating function evaluated at I xi. But there's a world of difference in where they're applicable. Remember that the moment generating function only makes sense for random variables that are exponentially integrable, at least on some interval around 0. On the other hand, the Fourier transform is defined for all probability measures, simply because the function e to the I xi dot x is bounded. And so the characteristic function is defined for all measures. At the same time, by this superficial observation, it carries at least as much information as the moment generating function. We'll see in a moment that you can recover the moments in a very similar fashion from the characteristic function as you can from the moment generating function. In short, the cost of upgrading our integral to allow complex valued functions is well worth the price of admission to gain access to all probability measures instead of just those that have exponential integrability. Let's state a few of the basic properties of Fourier transforms of probability measures. First, the Fourier transform of any probability measure evaluated at 0 is 1, and generally is a complex valued function which is bounded in modulus by 1. Fourier transforms of probability measures are always continuous functions. They're generally complex valued, but the conjugate can be achieved just by swapping the sign of the argument. And in particular, it follows from this that the Fourier transform of a measure is real valued if and only if that measure is a symmetric measure, which is to say that it assigns the same measure to any Borel set as to the reflection of that Borel set, negative b. In terms of random variables, that is to say, if x is a d-dimensional random vector, then its characteristic function is real valued if and only if x has the same distribution as minus x. And finally, smoothness of Fourier transforms equates with decay and integrability of the underlying measures. If our measure mu has kth finite moments for an integer k, then the Fourier transform mu hat is k times continuously differentiable. And in fact, its partial derivatives of order up to k can be computed like this. Let's prove these properties in turn. First of all, mu hat of 0, by definition, is the integral of e to the I 0 dotted with x, which is just 1, and mu is a probability measure, proving that mu hat of 0 is 1. More generally, the modulus of mu hat of xi by the triangle inequality for complex integrals is less than or equal to the integral of the absolute value of e to the I xi dot x against mu, but this is a complex number of modulus 1, and so we get, again, 1 as an upper bound here. Now, as for continuity, if xn is a sequence of vectors in Rd that converges to some xi in Rd, then notice that e xn, the trigonometric polynomial, is e to the I xi dot x, and since the exponential map is continuous, that converges to e to the I xi dot x for every x, which is e xi at x. So we have pointwise convergence of integrands, and we can therefore conclude by the dominated convergence theorem that the integral of e xn against mu converges to the integral of e xi against mu, since e xn and e xi are all uniformly dominated by the constant function 1. But that's mu hat of xn, and that's mu hat of xi, and so we get continuity of the Fourier transform. As for conjugates, we just compute that the conjugate of mu hat of xi is the integral of the conjugate of e to the I xi x, because the conjugate of an integral is the integral of the conjugate. But of course, that's the integral of e to the minus I xi dot x, and as we've noted before, that's just e minus xi, and therefore we have mu hat of minus xi as claimed. Now for the statement about real-valued Fourier transforms, if mu is a symmetric measure, and we choose a random vector x with that distribution mu, meaning that it has the same distribution as minus x since it's symmetric, then mu hat of minus xi is the characteristic function of x at minus xi. And that's the expected value of minus I xi dot x. But because x has the same distribution as minus x, and this expected value is a function of the distribution of x, we can change x to minus x without changing the value here. But of course, that's just mu hat of xi. On the other hand, as we just showed here, mu hat of minus xi is the same thing as mu hat of xi conjugate. And so if mu is symmetric, we do indeed have that mu hat is its own conjugate, meaning that it is real valued. Now for the converse, suppose that mu hat is known to be real valued. Let's let nu be the measure which assigns to each Borel set B the measure mu of the reflection, minus B. Well, basically mimicking the calculation we just did, it follows that mu hat of minus xi is equal to nu hat of xi for every xi. But that means that mu hat and nu hat are equal as functions, and as we saw on the first slide, it follows from there that mu equals nu, which is to say that mu is a symmetric measure. So we have left to prove the statement about smoothness. Well, we simply note that the integrand e to the I xi dot x is of course an infinitely smooth function of the variable xi for fixed x, or vice versa, and its derivatives with respect to the components of xi can quickly be calculated as such. So what we'd like to do is integrate both sides of this equality with respect to mu, and we will have proved the statement if we can show that this is equal to this. Indeed, that will show that these derivatives are at least well defined, and by induction, since we can get back one step by integrating by the fundamental theorem of calculus, we'll also get that all of those partial derivatives are continuous. Well, the well-defined bit here is just from the assumption of the theorem that these are all finite. But in fact, in order to exchange this integral and these derivatives, we need more than that this side is finite. We need by our differentiation under the integral sign, a number of conditions to hold. Some of them are just about measurability and well-definedness almost everywhere in the two variables, but since this function and all of these ones are perfectly nice continuous functions everywhere, the only condition that we really need in order to use differentiation under the integral is that these derivatives, pointwise, are uniformly bounded, at least for xi in some bounded set in Rd, by some L1 function g. However, this is very straightforward from the initial statement because this function has modulus 1, and so the modulus here is just equal to the modulus of xj1 up to xjk. Well, that's independent of xi, so we don't need to worry about this xi only being in a compact set, and it is in L1 of mu by the assumption of the theorem. And that's just because the Euclidean length of the vector x is, of course, greater than or equal to the absolute value of each of its components, and therefore the integral of x to the k is greater than or equal to the integral of any product of k of the components. But by assumption, that's finite, which shows that all of these are finite. And so this function here, which we assumed to be L1 in the theorem, gives us our uniform dominating function to conclude differentiation of the integral sign and conclude this statement about smoothness versus integrability of the Fourier transform of a measure. Now let's proceed to another very elementary but incredibly useful property of Fourier transforms, that is, how they relate to convolution of measures. If mu and nu are two Borel probability measures on Rd, then the convolution has as its Fourier transform the pointwise product of the Fourier transforms of mu and nu. The proof of that is very simple once we recast it in terms of the equivalent statement for random vectors. If x and y are independent random vectors, meaning that the law of the sum is the convolution of the laws, then the characteristic function of the sum is the product of the characteristic functions. And to prove that, we just note that the characteristic function of the sum, written here, can be factored since e to the I xi dot x plus y is e to the I xi dot x times e to the I xi dot y. And since x and y are independent, these two functions are independent. And we therefore have a theorem that says that since the whole thing is L1, each of the two terms is L1, and the expected value factors, thus concluding the proof. We also have this useful statement here, that if we shift a random vector by a fixed vector v and dilate it by some real number a, then the effect of that on the characteristic function is just to pull out an e to the I xi dot v and to scale xi instead. In fact, the adding v part follows immediately from this statement right here, since we can view v as a deterministic random vector, and of course its characteristic function is just that. And I'll leave it to you to write down why the a can be shifted between the x and the xi. Example time. Here are a few examples of standard kinds of distributions we've seen come up and their characteristic functions. If u is a uniform random variable on an interval from a up to b, then just writing down the integral definition of the Fourier transform, the characteristic function is given right here. As a special case of this, let's take the case where a equals minus b, so we have a symmetric interval. If we have a uniform probability measure on a symmetric interval, then that is a symmetric probability measure, and so we should expect, by the theorem we proved a moment ago, that its characteristic function is real valued. And indeed it is, because this reduces, as you can easily check, to the sinc function. Of course, the sine function goes to 0 fast enough at 0 that dividing here does not affect the continuity, in fact, infinite smoothness of this function. How about a Poisson distribution with some rate lambda? Well, the characteristic function is the expected value of e to the I xn, and we'll just use the probability mass function of the Poisson law in order to write that as this sum. Of course, we can simplify that and collect some terms, and that simply becomes this kind of double exponential function here. That's the characteristic function of the Poisson law. Now, a continuous law which is related to Poisson, for reasons that we will explore a little later, is the exponential. If t has exponential distribution with rate lambda, then its characteristic function is of course just given by this integral. Now there are a couple of ways we can attack that integral. One is to write the trigonometric polynomial as a trigonometric polynomial. Now break up this integral in terms of its real and imaginary parts, and we have to do integrals of e to the minus lambda x cosine of cx type terms, which we can compute using a double integration by parts, and gosh, I'm getting tired just saying that out loud. The alternative is to boldly barrel ahead and combine this as a single exponential. Now, it's an exponential with a complex rate, but if there's any justice in the universe, this should integrate just the same way that a real valued rate there does, provided that the lambda is positive, and that does indeed turn out to be true. The solution here is lambda over lambda minus IC. Now that looks a lot like the moment generating function of the exponential, but that only makes sense when t is less than lambda, where it blows up. On the other hand, this formula is valid for all c in R. So there's a visceral demonstration of how the characteristic function is better behaved than the moment generating function, even for very nice distributions like the exponential. And let's look at one more quick example right now, the bilateral exponential. This is a random variable that has density given by the exponential density over 2 on the right half line, and the reflection of that on the negative half line, right here. Well, we can compute the characteristic function of that just from the integral, and we can go ahead and do the integral exactly the same way, or we can be clever and write this as an integral from 0 up to infinity plus an integral from minus infinity up to 0. The integral from 0 up to infinity is exactly the integral we just did, except with a factor of 1/2 in front. And the integral over here will actually give us exactly the same answer again, up to exchanging x with minus x, which we can translate to exchanging xi with minus xi. And so when all is said and done, that's going to give us this expression here. And that simplifies nicely by putting over a common denominator, noting that lambda minus ixi times lambda plus ixi is just lambda squared plus xi squared. The result becomes this function here, which up to a factor of pi is its own probability density, known as the Cauchy distribution. We'll come back to that in the next lecture. I'd like to now do two more informative examples. Let's consider a discrete measure like a Bernoulli, but in order to make things work out a little nicer, let's take a symmetric Bernoulli, also known as a Rademacher, a random variable which takes the values plus and minus 1, each with probability 1/2. That's a symmetric distribution, and in particular that means that its expected value is going to be 0. Indeed, it's 1/2 times minus 1 plus 1/2 times 1. And just for good measure, let's report its variance, which is 1/2 times 1 squared plus 1/2 times minus 1 squared, which is just 1. Now we can compute its characteristic function very quickly. Again, it's the expected value of this random variable, which again only takes two values. Those values are e to the I xi times 1 and e to the I xi times minus 1, each with probability 1/2. But that simplifies. E to the I xi plus e to the minus I xi over 2 is just the cosine of xi. So the cosine function is the characteristic function of a distribution, this one. And by the uniqueness theorem that we started the lecture with, it's the only one that has this as its characteristic function. Now let's do a fun calculation here. Suppose that I take a sequence of independent Rademachers and I add them up. Take Sn to be the sum of n IID Rademachers. What can I say about the characteristic function of that sum? Well, I have a result that tells me that the characteristic function of a sum of two independent random vectors is the product of their characteristic functions, and I of course can do induction on that to see that the characteristic function of a sum of n is the product of the characteristic functions of all n of those, and so that's going to give this. But those are IID. They all have as their characteristic function the cosine function. Now we might be interested in what happens to the sum Sn as n goes off to infinity. But of course, we've considered not just the sum, but a rescaled sum in our theorems, for example, the strong law of large numbers. So let's rescale it by some as yet undetermined Bn, Sn over Bn. Well, by the rescaling calculation that we had on the previous slide, this is then just going to be the cosine of Xc over Bn, all to the power n. Okay, now what can we say about that in the limit as n goes to infinity? Well, we could, for example, take the Taylor expansion of cosine. And I'm not sure how much information that's going to give us, but one thing it does tell us is that this is 1 plus stuff. And that stuff is going to be, to leading order, positive. So we can take the logarithm here, at least for small xc. And now we can Taylor expand a little more carefully. Taylor's theorem tells us that the function log of cos t, which is certainly smooth for t less than pi over 2 in absolute value, has this expansion to first order with precise error term. That is, it's this affine function plus a second order correction, which is exactly equal to 1/2 the second derivative at some point in between 0 and the evaluation point t. Now we can calculate these derivatives. The derivative of log cos is minus tangent, and so the second derivative of log cos is minus secant squared. If we evaluate log cosine or tangent at 0, we just get 0. And so these two terms drop out. And thus, the log of the characteristic function of Sn over Bn at c can be written as n times minus the secant squared of eta over Bn times c squared over Bn squared for some eta in between 0 and xc. So that's as much as we can say without more precise information about Bn. But let's consider the case that we're familiar with, when Bn grows linearly with n. Well, since Bn is blowing up, eta over Bn is going to 0, and this goes to minus secant squared of 0, which is minus 1. But here we have Bn squared, which is n squared in the denominator, and the n in the numerator isn't enough to dominate that, so the whole thing just goes to 0. And so we can conclude that the log of the characteristic function of Sn over n converges pointwise to 0. In other words, the characteristic function of Sn over n converges to 1, and that is the characteristic function of the point mass at 0. So this is consistent with our knowledge that Sn over n converges as a random variable to 0, almost surely. That's the strong law of large numbers. But we could take Bn to be another sequence tending to infinity, but slower. Let's take Bn equal to the square root of n. Well, the same calculations work over here. This is still going to go to 0, so this is going to go to minus 1. But now, Bn squared is n, canceling that out exactly. And so now we're going to get that the log of the characteristic function of Sn over root n at xc converges to minus 1/2 of xc squared. That is, this rescaled characteristic function itself converges pointwise to e to the minus 1/2 xc squared. And that leaves us to wonder, is this the characteristic function of some probability measure? That would suggest that the law of this random variable might converge to that measure. Well, we'll leave you today with one more calculation. Let x be a standard normal distribution, mean 0, variance 1. Let's compute its characteristic function. Phi x is defined as usual as such. Now we could write that out as the integral of the Gaussian density, and then we could attempt to evaluate this integral, perhaps by writing this in terms of its real and imaginary parts and doing some kind of integration by parts repeatedly. I don't want to even try that. Instead, let's note that this has finite moments of all orders, and so we've therefore proved that the characteristic function is in fact C infinity. In particular, it's at least C1 smooth. And so what I'm going to do is develop a differential equation that it solves. We will solve that differential equation to compute the characteristic function? Well, note that, again, by something we proved before, the derivative of this characteristic function can be computed as such. But notice that that has the form expectation of x times f at x for some nice function, f. Now, earlier we proved Gaussian integration by parts, which tells us that if x is a standard normal distribution, the expected value of x f at x is the same as the expected value of f prime at x. For that, we needed that x f at x, f prime at x, and f at x were all L1 functions. All of those statements are true because of this. So let's compute that derivative. It's as such, and that means that the derivative with respect to the xi variable of phi x can be alternatively written as minus xi times phi x of xi. Now that is a very nice first-order linear differential equation, which you should be able to solve very quickly. And the solution is that phi x of xi is equal to a normalizing parameter, which is just phi x of 0, times e to the minus xi squared over 2. And we know that all characteristic functions are 1 at 0, and there we have it. The characteristic function of a standard normal is indeed e to the minus xi squared over 2, which looks a lot like the Gaussian density itself. It's just missing a constant. So, from the last two examples, we've shown that if x1 through xn are IID Rademacher random variables, then their standardized sum, the sum divided by the square root of n, has characteristic function which converges pointwise to the characteristic function of a standard normal distribution. Of course, you already know that that doesn't have that much to do with the Rademachers. That is just a special case of the central limit theorem, and we're going to use the characteristic function as a key tool to prove our first statement of the central limit theorem in another lecture or two. But first, we need to understand a little bit more about the regularity properties of the characteristic function, and in particular, how it behaves under weak limits of probability measures.